Today we're going to be looking at acceleration. So far we've looked at displacement and we've looked at velocity, where velocity was the rate of change of displacement, so how quickly your position changes. And now we're going to look at how velocities change, and a change in velocity is called an acceleration. So by the end of this, we should be able to calculate the acceleration of objects. Sorry about the unpleasant picture here. That's a picture of a flea. And the reason that's there is, I think, of almost all animals, they sort of exhibit the greatest acceleration because they can do massive jumps. They can go from a very slow speed, or stationary, to moving very fast in a very short time. So, a picture of a flea. Anyway, let's move on. So last time I asked you to look at displacement or distance time graphs. I've got an example here. I've got a distance time graph and three things are happening. I've got section A here, section B and section C. Can you just pause this for a second and write down what you would say was happening at each stage? Okay. So, assuming you paused and actually followed my instructions there, you should have written down a few things. I'm going to work in reverse order. I'm going to start with section C. And section C, well, first thing you notice, it's a straight line. And anytime it's a straight line, you would say the word constant. So it's a constant something. And in this case, it will be a constant velocity or a constant speed. Probably should say speed on this one because it's a distance, not displacement time graph, but that actually doesn't matter for these ones. So constant velocity. And the reason it's a straight line is that every second that passes, the distance increases by the same amount. And that's really what our definition of a constant velocity is. You can't say whether this is fast or slow without having a scale on here. What you could do, and I'll just draw another line. Let's say we had a line like this one, and I'm not going to put a letter next to it. This line is also a constant velocity, but slower than this one. So the gradient tells you about the speed, and the steeper it is, the faster it is. But you can't just look at a line without any numbers on the graph and actually say it's fast or not. These could be two very slow things. It's just that this line is slightly faster than that one. And then section B, well, each second that passes, it doesn't move. So a horizontal line on a distance or displacement time graph is going to tell you it's stationary. And then this is why I'm talking about this today, section A. Now, it's getting steeper and steeper and steeper. The gradient's getting bigger, and the gradient, remember, tells you how fast you're going. So this is showing an object that is getting faster and faster and faster and faster. So this is what we would call an acceleration. Okay, so let's now go on to talk about acceleration. You'll see I skipped something there. We're going to look at that in a later lesson. Okay, so let's just start with common sense. You know what an acceleration is. It's when something gets faster, or when something, well, actually you might not know this bit. It's also an acceleration if something slows down as well. Normal people would just call that a deceleration, but we can call it a negative acceleration. It doesn't really matter for us. Because acceleration is a vector, just like velocity was, it has direction. So a positive acceleration would normally mean speeding up, and a negative acceleration would mean slowing down. Now, in everyday language, like I just said, it means just go faster. But for us, we're going to use a more technical definition. And it's similar to the definition from the other day of velocity. It's to do with how quickly something happens. And the way we phrase that is we say it's the rate of change of the velocity. So I'd like you to take that down. So you can pause this if you like. Acceleration is defined as the rate of change of velocity. And then in brackets after that, I've got speed or direction. Okay, so this little bit at the end is quite important because it means that you can accelerate in two ways. You can accelerate by changing your speed, and that's what we're used to. You're in a car and the car goes faster, you're experiencing an acceleration. But because acceleration is defined as the change of velocity, you can also accelerate if you change direction. This is why it feels exhilarating if you go round a corner fast in a car, because although your speed might not be changing, your velocity is. And for that to happen, there has to be a force, and we'll come on to that later, but that's what makes you sort of give that sensation of something happening, and it's what roller coasters rely on. A lot of roller coasters don't go particularly fast. A lot of fairground rides don't go particularly fast, but they give you the sort of the thrill and the excitement by making you experience large accelerations, and they do that by making you change direction very quickly, which is an acceleration. So you need to remember that an acceleration could be a car that's not moving or moving slowly, I thought that was going to move, speeding up. It could be a car that's moving along at constant speed and then someone puts the brakes on and it slows down to a stop. Or it could be the car changing direction. All of those would be accelerations. Now, the exam board is going to try and not catch you out with this, but they know that most people don't think about a change in direction being an acceleration. So they ask about this quite often. The sort of thing they ask might be, how can a car go round a roundabout at a constant speed but still be accelerating? And the way you'd answer that is you would say, okay, well, as it's going around the corner, its direction is changing. And if its direction is changing, its velocity is changing. And if its velocity is changing, it's accelerating. So it might be worth stopping and making a note of that quickly as well. And if you want to hear that again, you can just rewind. Okay, so that's what acceleration is. The next slide just simply has some key points. If there's anything you've not taken down, stop this now and take these down. So when the velocity of an object changes, it's accelerating. A change in velocity can also mean a change in direction. And then the final bit, even if the speed stays the same but the direction changes, it is being accelerated. Okay. So what about actually quantifying, putting a number on an acceleration? How could you tell someone that one thing is accelerating more than another? Skip that. Okay, I mean, you might be in the market for a car in the future. And one of the things people are interested in with cars is which one has the best acceleration. So, this might be an example. I've got two cars here. A Honda Accord, it goes to 60 miles an hour in 7.8 seconds. Whereas this Lotus Elise gets to 60 miles an hour in 5.8 seconds. So the thing to notice here is that the top speed, well, it's not the top speed, but this number here, this speed, is not the important bit. Both cars can get to the same speed, but the Lotus gets there in less time. And the shorter the time is for the speed to change, or velocity to change, the greater the acceleration. So there you go, taking 2 seconds less means the Lotus has better acceleration. So this means well, it doesn't mean anything, but it leads us to think about that when we wanted to come up with a definition for velocity, we said it was the rate of change of it. And to work that out, we said, well, how much did the distance or displacement change in how much time? So we divided it by time. And we do the same thing for acceleration. Acceleration can be calculated by working out how much velocity changes in a certain time. So it gives us this equation. Acceleration is the change in a velocity divided by the time taken for a change. And I mean, from maths, you should find this quite simple, but look, if I make this number at the bottom larger, so it takes longer, that makes the acceleration smaller. If I make this number smaller, it makes the acceleration bigger. Now, as always, when I show you these, we need to know the units. So if you take this down, you could sort of just jot down what you think the units are now, and then I'll show you. Okay, so here you go. Right. So, change in velocity is in meters per second. They expect you to know that. You probably won't ever get a mark on an exam for knowing that. It's just taken for granted. Same for time taken for the change. It's going to be in seconds. But the acceleration is something that might be new to you. The unit is meters per second squared. The way we get to that is that we've got meters per second, which is the change in velocity, and then we divide all of that by seconds, which is the time taken for the change. So it's meters per second per second. And the shorthand way of saying that is meters per second squared. It also, it's worth thinking about what that really means. So say I tell you something like, if I were to jump, I don't know, jump out of this window out here, and I started falling, the acceleration on Earth is 9.8, roughly, meters per second squared. What this means is that every second that I'm falling, I go 9.8 meters per second faster. So if I jump off a very high building, hopefully I'm going to jump into water or on a crash mat or something, or a bungee jump. After 1 second, I'd be going 9.8 meters per second. After 2 seconds, I'd be going almost 20 meters per second. 3, I'd be going almost 30. That's what this meters per second squared means. Now, I don't know about you, but I don't normally want to write down this sort of full expression. So there's a shorthand way of doing it. We're going to use A for acceleration, T for time for change. And the change in velocity, there's 2 ways of doing it. It depends how comfortable you are with maths. So I'll show you this. Well, I'll show you both ways. So the equation can become acceleration equals the change in velocity. Now this looks unusual, we've not met this before, but really the change in velocity is like the final velocity, the speed you end up at, minus the speed you started with. So we use v for the final velocity and u for the initial velocity. And that just tells you the change. Now quite often you start from something that's stationary, so this initial velocity would be 0. But for completeness we've included that there. There is, I think, a more elegant way of writing this, and we could write acceleration equals delta v. We could put delta t as well, but I'm not going to today. And you probably have met this in maths. It means the change in. So acceleration is the change in velocity divided by the time. Either of those are perfectly good, but it's worth sticking at with one or the other. And it's less work than writing down the whole thing. So if you haven't taken any of that down, there is that as a summary. Pause this, take a note of it. Okay, so before we do anything else, we can have a couple of examples with this. I do want to just highlight something about this equation, that you do need to be very careful when you've got this v minus u. You want to work that out first of all, or if you insist on entering it like that into the calculator, make sure that this bit's in brackets. Make sure that bit happens first. Otherwise you're going to be in trouble. You'll get the wrong answer. You run into problems with BIDMAS, I think you call it. We called it BODMAS when I was at school. So, right, let's have a look at the sort of example that you might get. Okay, so this is quite a simple example. A rock is stationary at the top of a cliff. It falls off the edge. 3 seconds later, its speed reaches 30 meters per second. Calculate the rock's acceleration. All right, so I'm asking you a stupid question at first. What's its speed? I've just said it's stationary. Yes, I was trying to work out whether I'd spelled stationary right. The reason I've done this is that because we've said that it's the change in velocity and we say it's the final minus the initial velocity, some people get stuck if the question doesn't tell you what the starting speed is. But it does. You just have to notice that stationary means that it's still, which means that the initial velocity or speed is 0 meters per second. Okay, so then I would annotate this 3 seconds later, so that's my final velocity. Over here we've got, oh, that's not a velocity. What am I talking about? Sorry about that. That's a time. And then I've got a final velocity of 30. So that's my v. Now this time it's quite handy. So because the initial velocity was 0, our change in velocity is going to be 30. So you could write that down. Have I got it on the page? I might have to just do this on here. So what I would write down is I would write A equals V minus U over T. I'm always going to write that down. I'm now going to substitute the numbers in. So it would be 30, the final velocity, minus, you don't really need to do this step, but I'm just doing it to be complete, minus 0, put it in brackets, and divide that by 3, making sure I do that part first. And then the final answer, 30 divided by 3, 10 meters per second squared. Now, only thing left to do is just think about rearranging this. So for many of you, you'll feel fine with this and you can just stop the video now and you can try the questions that I've put in the classroom assignment. If you want to have a look at maybe a different example, how you might approach it, I'm going to keep the video running and record another little example now. So let's say something asked you, it's got an acceleration of 10 meters per second squared, meters per second squared, and the time it took was 2 seconds. Okay, and someone asked you, well, okay, what was the change in velocity if it accelerated at 10 meters per second squared for 2 seconds? So for the change in velocity, I'm just going to put v down. I could put delta v. I'm going to put a question mark. So for this, where we're now changing the subject of the formula, I still would write the formula down first of all. So I'd write A equals, I'm being lazy this time, the change in velocity divided by the time. That would be okay. I'm now going to substitute the numbers in. So I'm going to say 10, the acceleration, equals the change in velocity that we're looking for, divided by 2. Now, I do this for 2 reasons. One is, if you mess up rearranging the equation, you get a mark at this stage for substituting the correct information in. The other reason is that often they use very simple numbers. So in this example, something divided by 2 equals 10. I'm pretty sure most of you would instantly just go, I know that. That's going to be 20. And you don't really need to do anything else. It's really quite straightforward. So you can do that just to see what's going on. But this, you might find the numbers are more complicated and you want to rearrange it to make sure that it works. So what you can do is use either the skills, sorry, the video's gone a bit weird, use either the skills that you've learned in maths about rearranging equations, or we could use an equation triangle. So in this case, the equation triangle, because V is at the top of the division, it goes at the top of the triangle. The other two go at the bottom. There's my triangle. And like normally, if I want to find something else, like in this case, the V, I would cover up the V and it tells me that I need to multiply together, because they're next to each other, the acceleration and the time. So that tells me that the velocity equals the acceleration times the time. So that is going to equal 10 times 2, 20 meters per second squared. No, it's not meters per second. Okay. If you have any more problems with this, make sure you message me or email me and I can give you some one-to-one help with it. But that's it. Now, could you go to the classroom and try and answer some of the problems?